All right, hey everybody. So we're going to do another example using partial fractions. And this one is a bit more complicated, so I've repeated the rules we have been using in this small series of videos. And here's the question we want to attack. We want to take this integral of this fairly complicated rational function, okay? And so I'm just going to go ahead and begin. I'm going to recopy this thing and then start applying the rules. Oops, something just shifted on me. Okay, then start applying the rules from above. So here is our integrand, right? So the whole job I have right now, I'm not even worried about integration. I'm only interested right now in how can I rewrite this fraction as another fraction, as a sum of a series of fractions that happen to be simpler, which make them more integrable for us. So let's look at what I have. My first factor, so luckily this one happens to be factored already, is an irreducible quadratic, right? There are no roots to x squared plus 1 in the real numbers, no number that's squared to be negative 1. So that means, according to the rules, I need to have a fraction over here with that in the denominator, right? So this is our second rule here, this last row, that if we have a irreducible quadratic, then we get that as a, this is the case where m equals 1, so we just have this first term here. And above it, we're going to put a linear term, right? And the constants a and b are what we're going to try to discover. Now, since I have a linear factor, but there's two copies of it, I need one fraction with a single linear factor with one copy of it, and here we'll have two copies of it. And these get their own constants, right? They get constants above them, the quadratics get linears above them. Okay, in their numerators. So now what we're gonna do is clear the denominator on the left by multiplying. We're going to do the same thing on this side. All right, so what happens? Well, we cleared it on the left, so we're left with simply x cubed minus 4x squared plus x minus 2. And over here, we distribute these two factors to each of these. When we distribute, for instance, to the first one, to the first term, the denominator is canceled with the factor of x squared plus 1, leaving ax plus b, and we have x minus 1 squared. When we multiply to the second term, all that's left is c. We've canceled this factor of x minus 1, leaving x squared plus 1 behind, but also one extra factor of x minus 1, because there was only 1 in the denominator. And then in the d term, the x minus 1 squareds get canceled, and we're left with x squared plus 1. Okay. All right, now we're going to do a mess of algebra. So first thing I'm going to do is just expand everything over here on the right side. So leave this for now. X minus 1 squared is x squared minus 2x plus 1. X cubed minus x squared plus x minus 1 plus dx squared plus 1. Let's keep going. I get a x cubed minus 2ax squared plus ax plus b x squared minus 2bx plus b plus, now I'm on this, cx cubed minus cx squared plus cx minus 1 plus dx squared plus 1. All right, let's double check for errors. Ax cubed minus 2ax squared plus ax, bx squared minus 2bx plus b, cx cubed minus cx squared plus cx minus, there's an error, that should be c. Right. I always check for errors in these long problems because it's really hard once you get to the end and realize something's off. And then again, I made an error here. This should be D. Okay, glad I looked. All right, now I hope we're correct. So now what I'm going to do is collect like terms. So for instance, x cubed, I'm looking for everything with an x cubed in it, and I see 2 of them. So we'll have a plus c x cubed. Let's go to x squared. I see this x squared term, this x squared term, this x squared term, this x squared term. So this is going to look like negative 2a plus b plus, nope, minus c minus c plus d x squared plus, let's go to the x terms. We've got this one, this one, this one. Okay, so that is a minus 2b plus c times x. And then finally our constant terms, what is left, we've got b minus c plus d, right? And so this expression on the right, this mess of an expression, should be equivalent to what's on the left, which means the coefficients have to be equivalent. For instance, the coefficient of x cubed on the left is 1, so that means if these are going to be the same polynomials, a plus c must be equal to 1. We must have that negative 2a plus b minus c plus d is equal to negative 4, because the coefficient of x squared on the left is negative 4, so the coefficient on the right must be equal to negative 4. A minus 2b plus c, the coefficient of x has to be equal to 1, and our constant should look like negative 2. Okay, so this is a mess. We've got four variables in 4 equations, so it's a big system of equations. There's a couple tricks here we can use to sort this out, though, and make it a little bit easier on ourselves. First of all, looking at a plus c equals 1, I notice that over here I have an a plus a c. They must be equal to 1, so this I can substitute, right? I could rewrite this a plus c minus 2b equals 1, and this becomes 1 minus 2b equals 1, which clearly means b is equal to 0. Right, so there's one simple thing we can do to make this a bit easier. So let's rewrite what we have now. If b is equal to 0, this equation becomes 2a minus c plus d equals negative 4. This one becomes negative c plus d equals negative 2. Notice this negative c plus d equals negative 2. I can replace the negative c plus d. So I have negative 2a minus 2 equals negative 4. Negative 2a equals negative 2, or a equals 1. Okay. Well, if a equals 1, c must be equal to 0. And what does that leave us with? D has to be equal to negative 2, right? By putting 0 in for c. And there we have all of our variables, right? There's another trick some people like. You can, in this first line up here, once we clear the denominators, I can let x equal 1, right? Notice that would make these two factors both 0. We get, putting in 1 for x, we get 2d on the left, and you simply 2d on the right, and you compute the left-hand side, and you can get d. You'd still have to do this expansion or some other tricks to get a system of equations for the rest, so I usually just go ahead and do it, but some people like that trick. It would get us d a little bit quicker, perhaps. You can decide which route you like easier. In any case, now we have our coefficients for our expression. So let's go ahead and put those in. Let me just copy this so I can put those in. So let's see. All right, get rid of those stray marks. So what do we have? Well, A is 1, B is 0. So this first fraction is just x over x squared plus 1. C is 0, so this whole thing disappears. And D is minus 2. So this will be minus 2. And let's just move that all over. So now we have a new way to write this rational function. So now let's go back to our integral, right? That was the whole reason we did this. We wanted to compute the antiderivative for this ugly rational function. All right, so now what it means I can write it as is I can integrate over these two fractions. And of course, I can separate this into these. All right, now we still have to solve these integrals, right? So in the last example, they were pretty simple, but these might take a little bit of work. They both look like they'll use, we can use substitutions. So over here, I can use the substitution u is equal to, oops, I meant to write x squared plus 1. I was thinking to the next step, which means 1/2 du is equal to x dx. And over here, I'm going to use the substitution v is equal to x minus 1, so dv equals dx. This is a simple enough substitution. If you've been practicing substitution a lot, you may not even need to use it here, but it's fine to use it if you want to. All right, so let's see what happens with these substitutions. This first one, oh, sorry, I misread my writing and thought something was wrong. So I've got a 1/2. I always take my constants to the front. The x dx gets substituted as du with that 1/2 I already put out front. And my denominator is u. And then here, I might as well take that constant out front. And I've got 1 over v squared. That's actually, yeah, we'll write it like that. It's fine. dv. So now we've got the natural log, the antiderivative of 1 over u, minus 2. Let's just write this way. Now I can take this antiderivative, 1/2 natural log of u minus, let's see, we'll have 2v to the -1 divided by -1 just gives us an extra negative sign, so I can make that positive. And there's my plus c. And then I just have to put back in the expressions for x. Let's see, u was x squared plus 1. I guess we don't really need the absolute value there, but it doesn't hurt to write it. And then v was x minus 1 to the -1 plus c. Okay, and there we have it. That is the antiderivative of this mess of a rational function. As you can see, it does take a bit of work, right? And there's quite a bit of work we did to get here. There's a lot of algebra. And even once we get through all that, we still have to take the derivatives, right? So these problems are not, let's say, short, but the steps in between are all the kinds of things we should be able to do with some practice. This is going to be a place where organizing, being a little bit neat, being clear even to yourself, right? Not taking shortcuts, for instance, circling all these as I went so I didn't have to go searching through my algebra to find the constants when I needed them. Okay, I will stop there. Thanks, everybody. I will see you next time.